In this video, I'm going to be talking about fluids and pressure, and we have two example problems to build up the concepts and figure out how to do some of the calculations to solve for some stuff with pressure, forces, area, and all of those sorts of things. Our first question is in blue over here. We have a cylindrical container with a radius of 0.3 meters and is filled all the way up with water. What pressure is applied to the bottom of the container if it is 40 centimeters tall? So let's go ahead and draw a little diagram. So there's our cylinder. We have a radius of 0.3 meters. It's filled all the way up with water. So we can kind of shade that in a little bit. And it has a height of 40 centimeters. I'm going to go ahead and divide that by 100 and make that 0.4 meters. So everything is in my standard unit of meters. And then from there, we are looking for the pressure. Now, a couple things we know about this problem is that we do know the type of a liquid, which is water. And with water, we know that the density is 1,000 kilograms per meter cubed. And then from there, I think that pretty much covers our known variables. Now, if we're looking for the pressure, there are different ways to find pressure, but one of the main formulas that you would utilize is pressure equals force divided by the area. So that looks like one that we're definitely going to start off with. Now, if we're looking for the force applied by the fluid, we know that force is equal to the weight of the fluid pushing down on the bottom of the container. And then we have the area of the bottom of our cylinder, which is basically the area of a circle, which is pi r squared. Now from there, we probably need to make some more substitutions. I do know g because it's always 9.8, and I do know the radius. I do not know the mass. So because I don't know the mass, I know that the density of an object is mass over the volume. So if I go ahead and rearrange that, then rho, the density, times v equals the mass. So I can go ahead and do a little substitution there and take this and slide it into my numerator. So now I have rho Vg over pi r squared. And then from there, what we can do is we can make one final substitution, and that will simplify things for us quite a bit. And that substitution is going to be using the volume of a cylinder formula. So we have the volume of cylinder equals pi r squared times the height of the container. And we like that because the pi r squared in our numerator and in our denominator are then going to be canceled out. And that leaves us with a simplified version of our formula, which is rho hg. And from there, we can just simply plug in some numbers and easily solve for pressure. So we know our rho for water is always 1,000. We know the height of the water is 0.4 meters, and we know the constant g is 9.8. So if we go ahead and take the product of those three, we get 3,920 pascals. Now, I personally did a lot of those substitutions there to kind of show you where they came from and the different ideas that were involved. But oftentimes you can actually kind of jump straight to this final formula, and that's going to simplify things for you. And then you could have just popped these last three numbers in and then found your pressure. So let's go ahead and clear some room and then solve for our second problem. Now for our second problem, we have a liquid with a specific gravity of 1.3, and it says, what is the pressure at a depth of 0.5 meters? Now, this one feels a little bit trickier to me, although it isn't actually, because it doesn't seem like it has a whole lot of number values to work with. So the first thing we're going to take a look at is the specific gravity of 1.3. And the value of 1.3 is always a ratio that is the density of the liquid over the density of water. And we know the density of water is always 1,000 kilograms per meter cubed. So it's basically an indirect way of giving you the density of that unknown liquid. So we can go ahead and take 1,000 times 1.3, and then we have the density of our unknown liquid. All right, so let's go ahead and box that up, and we'll assume that's probably going to be useful a little bit later on down the road because we only have one more number of 0.5. So it actually kind of doesn't matter what kind of container it is because the pressure is just more dependent on the depth anyways. So if we have some kind of liquid, some kind of depth of 0.5 meters, the only thing that's actually going to be pertinent is the density of the liquid and the depth. So if we take our formula from earlier, which if you remember was rho hg, which a lot of times is rho gh, but it's all the same anyways because you're just finding the product to find that pressure. And we have a value of 1,300 for our rho. We have a height or depth of 0.5 meters, and we have the constant of 9.8. So just as we did with the other problem, simply find the product of those using your calculator, and we got 6,370 pascals for the pressure. So for this one, pretty simple calculation-wise. The one new concept that added to the first one, that added to the first problem, was this specific gravity idea, taking the ratio of these numbers over here. So I hope that was helpful to you in introducing some basic pressure and fluid concepts and calculations. Thank you for watching and listening.